Okay, so yesterday we gave a general description of how to define S matrix, okay, and in that process we also learned how to take into account the effect of mass denormalization and tadpoles. Okay. Today what we are going to discuss is some properties of this S matrix, in fact some properties that we need to prove, and that is unitarity. Okay. Now this is important because normally the proof of unitarity that people give for S matrix and string theory is based on a light cone gauge. Okay. In the light cone gauge you have a Hamiltonian, okay, which is Hermitian, and hence unitarity is straightforward. Okay. The problem however is that in a light cone gauge it is very difficult to show finiteness beyond a certain order, and in particular in superstring theory there are also additional contact term divergences which make the analysis in light cone gauge complicated. Okay. So while if one can make light cone gauge work to all orders in perturbation theory, then the unitarity proof will be more or less straightforward. Okay. That is not possible as yet, and that is the reason why you want to prove unitarity in the covariant gauge. Okay. And here you will see that there are many extra subtleties that you have to deal with. Okay. So what is the unitarity? Okay. So if we write the S matrix as 1 minus IT, okay, where T is the non-trivial part of the S matrix, okay, then S dagger S equal to 1, okay, this translates to I times T minus T dagger equal to T dagger T, okay, and I will write this in a slightly different way by inserting a complete set of states between T dagger and T. Okay, so this you can take as a statement of unitarity, and this is what you want to prove. Okay. So there are two steps to this proof. The first step, okay, will be to prove what is called Katkowski rules. Okay, I will not describe the complete proof, but I will describe what is involved in this. Katkowski rules are also sometimes known as cutting rules. Okay. So let me explain what these cutting rules mean. Okay. This is as in standard quantum field theory. Okay. So the first step is to draw Feynman diagrams with incoming state to the left, okay. This of course you can do in string field theory, because in string field theory you do have Feynman diagrams. Okay. Then we define a cut. Okay. So what is a cut? Cut is simply a line passing through the diagram. And it should separate the incoming states. Okay. So for example, if we have a Feynman diagram like this, Okay, we can draw many possible cuts. Let me use one cut that you can think of is just this one. Okay, but then you can also, so this is one possible cut, you can also describe this. This of course you can think of extending, okay, or this and so on. Okay, just something which separates the incoming state on one side and outgoing state on the other side. Okay, that's a cut. Okay. Now, given a cut diagram, there are rules for what it means. Okay. So that's the third rule. Okay. So a cut propagator, in a cut propagator, replace minus I times k square plus m square inverse by 2 pi okay. So k is a momentum that flows from left to right. Okay, I should say in a cut internal propagator. For external ones, there is no effect. Okay. So, for example, if you have a cut like this, okay, then for this line, you will replace the 1 over k square plus m square by this factor, and also for this line. Okay. Similarly, if you have a cut like this, then for these two, you will do the same. Okay. And the final rule is that the amplitudes that are to the right of the cut, they must get complex Hermitian conjugated. Okay, so these are the 4 rules that one has to follow to draw the contribution from any given cut diagram. Is this clear? Okay. So the Katkowski rules, okay, is a simple statement and that is that I times t minus t dagger is given by sum over all cuts of the diagram. Okay, so you take a contribution to t, okay, or to it, okay, which is a particular Feynman diagram, okay, and suppose you want to evaluate the contribution to it minus it dagger from that Feynman diagram. Okay. What the Katkowski rule tells us is that it is given by sum over all possible cuts of the diagram. So, for example, if we take this diagram and try to calculate it minus it dagger, what we will do is that you take all possible cuts of this diagram, calculate the contribution from these by using these rules that I have given here, okay, sum over all such cuts, and that should give the contribution to it minus t dagger. Is this statement clear? Okay, this is a statement in quantum field theories, okay, and this more or less proves unitarity, okay, and the way it proves unitarity is because the left hand side of course is this, okay, which is what you are computing. Okay. The right hand side, the sum over all cuts of the diagram, okay, this a given cut, okay, let us now erase these cuts and consider just one particular cut. Okay. So, take for example this cut, okay. This cut diagram has an interpretation that it is the product, okay, of T on this side, okay, and T dagger on this side. Okay. Why T dagger? Because the contribution from the right of the cut has to be Hermitian conjugated. So, this side computes T, the matrix element of T between these states and these states, and this side computes T dagger, the matrix element of T dagger between these states and these states. Okay. And then you are supposed to of course integrate over these internal momenta, okay, the d4k you have to integration over the internal momenta, but now instead of propagators, okay, you had these factors, okay, and these are precisely what provides the phase space integral. Okay. So, for this particular example, let me just write this. So, suppose this is carrying momentum k and this is carrying momentum p1 plus p2 minus k, okay, p1 and p2 are the two momentum which are coming in. Okay. Then you have an integral like integral d4k, and then you have 2 pi delta times of course the rest of the integrand. Okay. So, this rest of the integrand is what we interpret as T dagger n, okay, n T dagger. Okay. T dagger n comes from here, sorry, n T. N T comes from this side, okay, n being these intermediate states which are being whose momenta are being integrated over, okay, and this you can verify is the correct phase space factor. Okay. This is exactly the weight factor that you have to use to integrate over the intermediate momentum. Okay. So, this is the reason why the Katkowski rules are important, okay, because once you establish Katkowski rules, you have more or less established unitarity. There are some additional subtleties in gauge theories which I am going to mention later when we come to this. Okay, other questions? Okay, so now the question is how to prove it. Okay, we have described our algorithm for computing S matrix in string theory. Okay. The question is it possible to prove Katkowski rules for string theory, okay, because S matrix is given to us, the algorithm for computing S matrix is given to us. So, as I said, I will not give the full details of the proof, but I will give some general outline of how we go about doing this proof, and in that process we will also learn how to establish ultraviolet finiteness of the theory, okay, directly now in the momentum space. So, to prove this, we have to write the amplitude Okay. So, what I mean by this is the following. Okay. Let us again take this simple diagram that we had. So, yesterday we described how starting from a Feynman diagram of string field theory, you can get to the worldsheet description. Right. You take 1 over L0 plus for each of these and rewrite as integral ds e to the minus L0 plus, and those become the integration over the moduli space of Riemann surfaces. Okay. But this approach does not seem to be very suitable for proving Kaczkowski rules. So, for proving Kaczkowski rules, you will really think of this as a normal field theory, okay, in which you have momentum integrals. Okay. So, for example, for this diagram, you will label the momenta as you do in a normal quantum field theory. Okay. But in string theory, of course, you also have intermediate states, and you have to sum over infinite number of intermediate states, because these are all running over all possible string fields. Okay. And then you write the standard expression integral d4 k over 2 pi to the 4, or dk over 2 pi to the d. Okay. So, d is the number of non-compact dimensions in the theory, okay. And then the integrand, okay, which will have products of propagators and so on, and vortices. Now, it turns out that one key difference between a string theory and a normal quantum field theory, okay, is that in normal quantum field theory, that vortices, okay, are typically polynomials in momenta. Right? Think of scalar field theory or gauge theories, the vortices are always polynomial in momentum. Okay. In string field theory, on the other hand, the vortices actually have exponential factors in momentum. Okay. So, if we take a vortex of this kind, say 1, 2, 3 up to n, okay, with external momenta k1, k2, k3 up to kn, okay, then typically this vortex will have a factor of exponential minus c, okay, which I can write in a more okay, this is one of the factors in the vortex. This is not the only factor in the vortex. There are other factors involved, for example, polynomials in momentum, but it always has a factor like this. C is some constant, positive constant. Okay. This depends typically on the choice of these RGNs. Okay. For different choices, you get different values of C, but C always is a positive constant. Now, this has some good features, but some bad features. Okay. The good feature is that when you consider integration over the spatial components of momenta, okay, you can see that these factors, the fact that there is e to the minus c times ki vector square, makes these integrals ultraviolet finite. Right? There is no divergence from large momentum region because of these exponential separations. Okay. Whatever polynomial multiplies it, okay, the exponential factors will always take over. The bad feature, okay, is that it also has factors of C times Ki0 square. Okay, by Lorentz invariant, these come with positive coefficient. Okay. And this means that if we try to reinterpret this as an integral over Ki0 as we do in a normal quantum field theory, okay, these will diverge exponentially for large loop energies, right, because this goes as exponential plus C times energy square. Okay. So then the question would be how to handle this, okay, that you have to make some effort to define what we mean by this, how to integrate this. And the solution again is what we conventionally follow in quantum field theories, although not for this particular purpose, because quantum field theory you do not have factors like this. Okay. But the generic solution in quantum field theory to avoid all singularities, okay, is to define amplitudes, define momentum integrals by analytic continuation Okay. I will explain in more detail what it means, but this is basically what is called the weak rotation, right. We define momentum integrals by weak rotation, and that is what we will try to implement now. Okay. But how we implement it, I will describe the steps in detail. Okay. Are there questions? Okay, so this general procedure is implemented in several steps. The first, okay, so suppose the external momenta are Pi0 and Pi. Okay, this is the 0 component, this is the spatial component, these are all real. Okay. And of course, they satisfy the on-shell condition that Pi0 square minus Pi square equal to Mi square. Okay, so this is Lorentzian external momenta. So the first step, okay, will be to consider an amplitude with external momenta u Pi0 and Pi, okay, where u is some complex number. Okay, so you multiply all the external energies by some complex number u. Now you would notice that this you can do only if you have an off-shell formalism, right? Because once you multiply the external energies by some complex number u, okay, you no longer satisfy this. Okay, so you really need an off-shell Green's function. So at this level, you have already made use of the fact that we are off-shell. Okay, in string field theory, of course, there is no difficulty in defining amplitudes of this kind. Now, for imaginary u, okay, this is a special case. Here, external energies are all imaginary. Okay. So, here to define amplitudes, take all loop energies along imaginary axis. Okay, so all loop energies you take from minus I infinity to I infinity. Okay, this is the Ki0 plane. Is this clear? This is our definition of how this amplitude should be computed for imaginary U. Okay, just take everything along the imaginary axis. Okay. Now, let us check that this definition makes sense. Okay. First of all, because we are taking these loop energies to run from minus I infinity to I infinity, okay, the divergence problem that we had earlier is no longer there, right, because the vortices are all exponentially suppressed now. That minus Ki0 square has become plus Ki0 square, okay, because we are going along the imaginary axis. Well, minus Ki0 square remains minus Ki0 square, but that is now positive. Okay. So, there is no problem from infinity. Okay. But then you have to worry about whether there could be problem from poles of the propagator, right, because vortices have exponential suppression, but propagators are poles. Okay. Now, you can easily convince yourself that propagator poles are also not encountered along the imaginary axis, because when external energies are imaginary and loop energies are imaginary, all the internal propagators carry imaginary energy. Okay. So, 1 over p square plus m square for all internal propagators, okay, that strictly the denominator is strictly positive, right, because p square, okay, if 0 component is imaginary and the other components are real, then p square is strictly positive and m square of course is positive. Okay. So, this makes it clear that at least for u on the imaginary axis there is no problem in defining integrals of this kind by taking the integrals along the imaginary axis. Is that clear? This will be our starting point. But of course, eventually you want to get to u equal to 1, right, because that is where the real physical moments are. So, the third step is to now deform u to 1. This, what I am describing here. What I am describing here is analytic continuation, right. We have now defined what it is for imaginary axis. Now, I will show how to define how to use this to define the value at u equal to 1, right. That will be the definition of analytic continuation. Okay. So, what I am going to describe now is analytic continuation.
Imaginary plane is, complex.
Yeah, for imaginary values of u, right. This is a perfectly well defined integral, right. There is an analytic continuation here. I just substitute u imaginary, okay, and take all the internal energies to be imaginary, and then the integrand is perfectly sensible, right. So far I have not done an analytic continuation, I have just defined the result for imaginary u, right. Now I am going to do an analytic continuation to define the result for u equal to 1, starting from there. Okay. So, third step is to deform u to 1, okay, and we will do this along the first quadrant. So, in the u plane, we go from somewhere along the imaginary axis, we are trying to now deform to 1. Okay, we start anywhere on the imaginary axis and we want to go to 1. Okay. Now, the question is, as we take this to 1, how should we define our integral, okay, so that you finally what you get is really an analytic continuation of the result from imaginary u. Okay. So, first thing that we do, okay, which is different from what we do in a normal quantum field theory, okay, is that we do not change the ends of the integration contour. Okay. each loop energy integrals, okay, are still made to run from minus infinity at one end and I infinity at the other end. Okay. So, the end points are kept fixed at plus minus I infinity, okay. They are not allowed to move. Whereas, in a normal quantum field theory that you are familiar with, as you move you start tilting this integration contour. Okay. That is how you eventually end up with a real integration contour. Okay. So, the end points we are keeping at plus minus I infinity. Okay. But what is going to happen, okay, you see, as we deform u, the external energies are no longer purely imaginary, right? They have a real component and imaginary component. Okay. So, as a result, some of the poles of the some of the denominators that appear in the propagator may now actually become singular, may become 0, right? Because the argument that the denominator is strictly positive is no longer true. Okay. So, as you are deforming u, some of the denominators may diverge. Okay. And in this language, that means that some of the poles in the Ki0 plane, okay, when the external energies are imaginary, there are no poles on the imaginary Ki0 axis. Okay. But as u moves, as you change u, the locations of the poles in the loop energy integration space, loop energy space starts moving, okay, and these poles may approach now the axis of integration, okay, the contour of integration. Okay. If this happens, okay, then what you are supposed to do is to deform the contour away from the poles. Okay. You should not let the pole pass the contour, because that will be a discontinuous jump in the value of the integral. Okay. So, if any pole approaches imaginary Ki0 axis, deform the axis, deform the integration contour away. Okay. So, let me draw a figure here, okay, how a typical integration contour will now look when u becomes complex, general complex number. Okay. So, the integration contour, suppose the pole comes, okay, and crosses and ends here. Okay. Originally, the integration contour was along the imaginary axis, okay, but now it has to be like this. Okay. So, you do not want to leave the endpoints. The endpoints should be at plus minus I infinity, because otherwise you will not get the convergence from infinity. Okay. However, you must deform the integration contour to move away from the poles. Right. That is the procedure that you have to follow if you want an analytic continuation from imaginary axis to the real axis. Is this clear? Yes.
There is no case of pin singularity.
Yes, I was going to talk about that next. Okay. So, this you can do, okay, as long as you do not encounter a situation like this. Right. If there is a situation where there are two poles coming from two sides and pinching the contour, okay, then of course, as you move u further, you either have to cross this pole or you have to cross this pole, right? Otherwise, you cannot deform the pole contour anymore. Okay. So, the first result that one can prove is that the contour is never pinched as long as u is in the first quadrant. Okay, so you can indeed follow this, okay, all the way towards u equal to 1. Okay. So, finally, okay, we define the original amplitude as the u goes to one limit of this integral. Okay. So, this way you are ensured that there is no ultraviolet divergence, because the endpoints of integration are always starting from minus infinity and plus infinity, okay, for the energy integrals. So, the exponential factor at the vertices make all integrals exponentially suppressed as you go to large momentum. Okay. So, this is what in this momentum space integration form, this is the way you see the ultraviolet finiteness of the amplitudes. Okay. And we ensured that we can still use, okay, even though the momentum, the ends of the integration contours are at plus minus I infinity, okay, you can choose the integration contour in the interior appropriately, okay, to define the amplitude for real external energies. Okay, and that is the way you define. Okay, you define it for a general u first in the first quadrant, and then you define it as the u goes to one limit of the general expression. Is this point clear? So, given this definition, okay, one can now calculate IT minus IT dagger. This is what we want to compute. Okay. And here again what one finds is that IT and IT dagger are given by similar integrals with integration contours Okay. So, this gives a simple way to calculate. Well, it is not so simple, but nevertheless it gives you at least some way to start analyzing the difference IT minus IT dagger. Okay. Because what you have to do now is that IT and IT dagger are given by similar integrals by different contours. So, you start deforming the contour that contributes to IT to the contour that contributes to IT dagger. Okay. And the difference will be given by the sum of residues that you pick up as you are changing the contour from one to the other. Okay, this is Cauchy's integration formula. Okay. So, using that we calculate the difference between IT and IT dagger, okay, picking up the residues on the way. Okay. And after some long analysis, what one finds is indeed that Katkowski rules hold. Okay. That, so the result that one finds at the end is that IT minus T dagger is given by sum over all cuts of diagrams. Is this statement clear? Okay, as I said, this is not a small step, it requires some detailed analysis to actually compute IT minus IT dagger, but this is a general principle, okay, that you take the contours for IT dagger, and start deforming the contours from one to the other, and keep track of what kind of residues you pick up on the way. Okay, and then one can show that those residues can all be reorganized at the end as the statement that the result is given by sum over cuts of the diagram. Okay. So, this then establishes this relation IT minus T dagger equal to T dagger n T dagger n T. Okay. Unfortunately, this is not enough to establish unitarity yet, okay, because what happens is that because you are doing this calculation in a gauge fixed theory, typically in a Siegel gauge, okay, this analysis that I described is a result in the Siegel gauge. Okay. So, this sum over n that comes here, okay, this runs over all states of in the Siegel gauge in Siegel gauge. Okay. And as we discussed yesterday, that if you look at the Siegel gauge propagator, okay, there are of course physical states in there, okay, but there are also unphysical state poles, okay, and all of those will start contributing to this sum. Okay. So, that is not what unitarity should give, right. Unitarity should be a relation that this sum runs only over the physical states, okay, because those are two asymptotic states that you can produce in a scattering process. Okay. So, the second step in proving unitarity is to show that even though we have here the sum over all states in the Siegel gauge, that is what the cutting rules tell us, okay, that all states other than the physical states actually give vanishing contribution at the end. Right. So, that should be the second step of the proof of unitarity. So, step 2 is to show that contribution to okay. So, the first part that I described so far, okay, this could be done in principle in any quantum field theory, okay, not necessarily in string field theory. 10 minutes, I think I started at 40, right. Okay. Okay, so as I said, so far what I have done, okay, these cutting rules could be done in any quantum field theory, even though in normal quantum field theories you do not keep the ends of the integration contours fixed at plus minus I infinity, okay, because there is no need to do that. You can rotate the integration contour to lie along the real axis, okay, but you could choose to fix the integration ends at plus minus I infinity even in a normal quantum field theory. Okay. But what I am going to describe now is specific to string field theory, because this will require using properties of the string field theory. Okay. So, let us recall that the Siegel gauge propagator had the form I delta f, okay, and yesterday we wrote down an identity, okay, that QB hat delta f C 0 minus plus delta f C 0 minus QB tilde was G. Okay. If you do not remember the details, it does not really matter, because we are not going to use this directly. We will describe some consequences of this, okay, but this is the origin of the relation that I am going to write down now. Okay. So, suppose delta f has a pole at k square plus m square equal to 0, okay, for some m. Okay. Then near k square plus m square equal to 0, delta f has the following structure. Well, let me write I delta f. It has a structure of minus I k square plus m square inverse times some constant. Okay, let us call this xi naught. These are matrix. Okay, typically an infinite dimensional matrix, because string field, the propagator of course is an infinite by infinite matrix. Okay. But this has finite rank, okay, because you expect only a finite number of states at some mass m, okay, even though it is an infinite dimensional matrix. Now, what one can show using this identity that I have written here, okay, that this matrix sigma 0 or xi 0 follows some specific form, okay, and that is what I am going to write now. So, again this is somewhat straightforward algebra. You have to just plug this in, okay, this and manipulate things a little bit. So, what one finds is that this xi 0 has a structure where the following relations hold: qb hat Pa equal to 0, okay. So, these states are physical states because they are annulated by qb hat, okay. This was the physical state condition. Okay. These are not physical states, ur and dr, okay. And this notation minus 1 to the dr, okay, this one is just the Grassmann parity of dr. Okay, so it is minus 1 if dr is odd and it is plus 1 if dr is even. Okay, that is the notation. Is this statement clear? That this matrix xi 0, okay, has a decomposition in this form, okay, sum over states. This is here, these are physical states, okay, but here this is not physical, this is unphysical, this is pure gauge because this is qb hat on something, and here this is pure gauge, this is unphysical. Okay. So, when we cut a propagator, okay, a cut propagator I delta f will be simply replaced by 2 pi delta k square plus m square theta k 0 times xi 0, right, because the instruction is that you are supposed to replace this by 2 pi delta k square plus m square theta k 0. This will remain of course as it is, okay. This is a constant matrix, okay. So, we see now that if we want to prove unitarity, okay, what you have to prove is that even though in a cut propagator you are supposed to substitute this, okay, only this should contribute. This is the good part, right, because this really involves physical states, Okay. These are bad parts because this has an unphysical state on this side, this has an unphysical state on this side. Okay. So, let me be a little more specific. So, let us imagine that we have an amplitude, a cut diagram. Okay. We have a cut diagram with n cuts. Okay. Let us call this gamma L, let us call this gamma R. Okay. And we have cut. Okay. This runs from 1 to n. Okay. Then forgetting about these factors, okay, what we have is a factor of product I equal to 1 to n. Okay, and then we have basically a sandwich between gamma R and gamma L. You see, the gamma R and gamma L are reversed when you think of matrix elements, right? Because here the incoming is on the left, outgoing is on the right, but when you write a matrix element, right, the incoming is on the right and the outgoing is on the left, right? So that's why they are reversed here. So what one needs to show is that if we expand this out now, okay, it's a product of 3 terms n times. Okay, so there are 3 to the n terms if we only expand it out. Okay. One of these terms is just the product of these. Right? That's the one that you want. Okay, that's the one which will, if that was the only term which was there, that would establish unitarity. Okay. So what we need to show is that all the rest of the terms just cancel. Okay, they would have established unitarity. Is that clear? Okay, so only one out of these 3 to the n terms should contribute. Okay, rest should all vanish. Okay, in fact, it turns out that they do vanish. Okay, but they don't vanish term by term; they vanish after you combine that contribution. Okay, and for that you have to use the word identities for gamma L and gamma R. Okay, so in the maybe 7 minutes that I have, I'll just illustrate some simple examples. Okay, one will be a very trivial example, the other one will be somewhat more non-trivial. Okay, but that will illustrate the main point on how we do this. Okay, so let's consider some bad terms. So the first example, which is, as I say, the simplest bad term, okay, all but one are product over I, Pi, ABI. Okay. So here what we have is gamma R, okay, then product, say I equal to 2 to, or may I say, okay, I equal to 2 to n. Okay. And then 2 terms. Okay, this is one term in the expansion of this. Okay, that all of them from 2 to n it's this, and the first term I have picked the bad term. Okay. This is easy to see why it vanishes. Okay. Let's take this term. Okay, first take this term. Okay. And let us see, I should write the gamma L on this side. Okay. Let's see what are the states that are inserted on gamma L. What are the external states of gamma L? Okay. So, the external states of gamma L are of course these. Okay. These are all physical states, these are incoming states. Okay. So, there is no issue about them. Okay. And then the states which are coming from here. Okay. So, for this term, external states of gamma L are external states, true external states, then the BAIs, and QB hat B1R. Right? The external states which are coming from left of course are there, but other than that there is a BAIs, each of these are entering gamma L, and this one is entering gamma L. But this amplitude of course is 0, right, because this is an amplitude with all but one physical states and one pure gauge state. Okay, and yesterday we had seen that as a result of the word identity for gamma, okay, amplitudes of these kinds are 0, okay, all physical and one pure gauge. Is this clear? Okay, so this term will vanish. So this term will vanish because of the gamma L, and similarly one can show that this term will vanish because of gamma R. Okay, because now with gamma R you have an insertion of a pure gauge state. Okay. These are all physical and external states are all physical. Okay, maybe I will leave this as an exercise, the next one. All but 2 are PAI. Okay. So, all of them are of this kind, except that from two factors, say 1 and 2, we have picked this from 1 and the same term from 2. So, if we expand this out, there will be 4 terms, right, because 2 terms in each, take the product with another term which has 2, which is a sum of 2. So, there are 4 terms altogether. Okay. 2 of them will vanish trivially. Okay. 2 of them will vanish because what will happen is that on gamma L, in one of them, on gamma L you have physical states and 2 pure gauge states inserted. Okay. That vanishes again by the word identity that we had yesterday. Okay. And another term will have a similar feature for gamma R. Okay. But then there are 2 terms which are not manifestly 0, okay, because you could have, for example, okay, say in gamma L we insert this and this from the first term and this from the second term. Sorry, this is on gamma R. On gamma R we insert this from the first term and this from the second term. So, while this is pure gauge, this is unphysical, right? This does not get annihilated by QB hat. Okay, so this does not vanish. And similarly for gamma R, in one of them you have this term, in the other one you have this term. Okay, again it does not vanish. Okay. But what you can show is that of these 2 terms, okay, you can use the word identity that I derived yesterday to move the QB hats from one state to another state. Okay, because see, if we have QB hat, if all of the states are physical, okay, and you have two states, one of which is acting QB hat, okay, you can move QB hat from one to the other by using the same order identity that I gave yesterday. Okay. Using that, we can show that the contribution from these two bad terms, okay, which do not vanish by themselves, they actually cancel, okay, because you can move QB hat from one to the other and they eventually give you 0. Okay. And this generalizes to arbitrary products of this kind. Okay. However many bad terms you choose here, you can show that you can organize things in such a way that eventually they cancel pairwise. Okay. You just move the QB hats appropriately from one to the rest by using the word identity that I had yesterday, and then everything cancels. Okay. So that's the way you eventually establish unitarity. Okay. It's straightforward algebra, okay, but you have to just do it to see that it really cancels. Okay, so I think it is time to stop. Thank you.
Thank you very much. So again, discussion is postponed to tomorrow for further question and the solution of the exercise.
Okay.
And there are some announcements. Thank you very much.
Thank you.